I want to talk about neutrons and isotopes. So this actually took more time to figure out than people had realized. So again, when I start to look at elements in particular or a particular atom, I want you to remember that I'm always using either that P table, that dynamic table, or I'm going to be using Wikipedia. So let's go look at that. I think the study of isotopes is really, really interesting. There are so many incredible, analysis that we can do to try to get a sense of why does, different isotopes behave the way that they do here. So what we'll do here is that, let me remind you about a couple of things. We know that protons tell us what type of atom it is, but neutrons distinguishes the type of isotope one has. So this is another big definition. And you could have multiple isotopes that are stable. And that's one of the main reasons why they say all atoms are stable. You can have unstable isotopes. So what we typically say is that all atoms are called isotopes. And what that means here is that there's really two things here. There's typically what we call the common form. And the common form is what's found in nature. So if you go and, let's say, look for hydrogen, you'll find that there's 3 types of hydrogen, as we're going to be talking about right now. And then what you're going to find here is that these are the uncommon form, and these are less likely to be found in nature. And so some isotopes are so rare that the only way you really get them is that you have to literally use a nuclear reactor of some sort or a nuclear accelerator to create them. So it is the isotopes, excuse me, I should not say that. It is the different kinds of isotopes of an element that sort of drives the atomic mass number. Maybe drives is not the right word, but it's the only one, the only word I could think of at the time, at the moment. And so what you're going to find here is that this here, the listed atomic mass is the weighted average of all isotopes. So when you look at the atomic mass on the periodic table, it's about all of the possible isotopes. So probably the easiest isotope to start about is hydrogen. So let's go look at these guys. Let's look at the isotopes. It's not the way we spell isotope. So the isotopes of hydrogen. And what we're going to do here is that when we look at these isotopes, you're going to see that there are 3 of them. Okay. So I'm going to go get the hydrogen. And here's this guy right here. So this is hydrogen. Okay, so I got this off the P table, the dynamic table. And the one thing that you gotta look at is that, look at that atomic mass number. Right? When you look at this atomic mass number, is that, note that this is not a number that's exact. But what you find about this number here is that it's slightly larger than 1. So what that tells you here is that there are going to be hydrogen isotopes heavier than the number that's listed here. So what do I mean by that? So what I'm really saying here, and I'll ask this as a question, so I try to be as clear as possible, is that why is the mass of hydrogen not exactly 1? Why isn't it exactly 1? And so to make sure that you're following where I'm going with this thing, I want to remind you, maybe not remind, but remember that the proton number defines the atom. So if I want hydrogen, I can only have 1 proton because the atomic number here is 1. So it turns out that there are 3 isotopes of hydrogen. So there's hydrogen 1, 2, and 3. And so when you look at these isotopes, these are very famous isotopes, okay? Very famous isotopes. And what you find here is that hydrogen 1 is what we typically call hydrogen. Hydrogen 2 is called deuterium. And hydrogen 3 is what we typically call tritium. And so when you look at their atomic structures, what is it that we actually see here? Well, that means we got to calculate them. So if I look at hydrogen 1, that means it must have 1 number of protons. But you could see, if I look at the atomic mass, we say that it has an atomic mass of 1. Hydrogen 2 has an atomic mass of 2. And hydrogen 3 has an atomic mass of 3. So when you look at these guys and we start to calculate the details about this thing, remember, we only focus on what? The nucleus, because that's what isotopes are about. you could see that this has 0 neutrons, this has 1 neutron, and this has 2 neutrons. So when you're looking at this thing, you're seeing that the reason why this is all called hydrogen is that they all have what? 1 proton. So it's hydrogen. So when you look at the nuclei, you can see that this nuclei right here has only 1 proton. This one has 1 neutron here. This one has 2 neutrons. And this guy, of course, has to have 1 proton each. So you could see that the nuclei are heavy. And believe it or not, these guys they bond good with oxygen, and they typically are seen as heavy water. So then the question is this here. The atomic mass of hydrogen is a weighted average. What does that mean? The atomic mass is the weighted average of all isotopes. So when I go and I write hydrogen, then this means here is that the mass of hydrogen then has to be what? The mass of hydrogen plus the mass of deuterium plus the mass of tritium. But what do I mean by weighted here? And so what I'll do here is that I'm going to go share my screen with you, and this is what I see here. So what I do here is that I just type in a search, and I just did hydrogen isotopes. And if you click on the isotopes of hydrogen, I'm really interested in this table right here. Okay, I'm really interested in this table. So what that means here, I'm going to go back to my table, and then I've already copied the table, and this is what I'm seeing here. Okay, so this is my table. So check it out. So what you're seeing here is that what this tells us, it tells us about the abundances. So of all of the hydrogen that has ever been observed, you could see here that what? 99.9% of all hydrogen is the hydrogen 1. And you could see that hydrogen 2 is 0.1%, which is a tiny, tiny amount. And then hydrogen 3, you could see that there's trace amounts. And what this is telling you here is that this tritium here is what? It's actually radioactive. That's what this number right here says. But what you're seeing here is that what is the most common isotope that you find? It's that element. So what we say here is that the reason why, okay, so the reason why the atomic mass of hydrogen, I'm going to move this down a little bit. Is not exactly 1 is because of hydrogens 2 and 3. So because of this, you see that the mass of hydrogen is slightly more than 1. That's why that number is not exact. It's because there are trace amounts of hydrogen 2 and hydrogen 3. So every time you drink a little bit of water, you are drinking a little bit of hydrogen 2 and a little bit of hydrogen 3. So what we say here is that we say this here. Because hydrogen 1 is 99.99%. How do I say this a little bit better? Yeah, because hydrogen 1 is 99.99%, this implies here it's the most common isotope, of course, of hydrogen found in nature. Whereas, on the other hand, H2 and H3 are less common. So if you go looking for them in nature, that's what you find. So what you're going to see here is that there's some things that we should really think about here. So for light atoms, and one example is hydrogen, okay? The first 4 rows, let me be a little bit more specific. The first 4 rows of the periodic table usually have the most common isotope listed on the P table, the periodic table. So the one listed, so when you look at hydrogen, hydrogen 1, because it's closest to the one listed on the periodic table, that's what you get. You find that that's the most common one. After row 4, much harder to actually predict what is that.